For Physics 201. This is the last recitation before Exam 2, which goes over chapters 5, 6, 7, and sections 1 through 4 of chapter 8. This recitation will go through chapter 7 and 8 with 6 questions, and let's get into it. So first, chapter 7, question 16. You throw a 20 Newton rock into the air from ground level and observe that when it is 15.0 meters high, it is traveling upward at 25.0 meters per second. Use the work energy theorem to find A, the rock's speed just as it left the ground, and B, the maximum height the rock will reach. So here we write out all our things, then we find the work energy theorem is work total equals the kinetic energy final minus the kinetic energy initial. And if we go to the formula sheet, we can find that one right here. Work total equals the final kinetic energy minus the initial, which is also signified as the delta K, or the change in kinetic energy. So we write that down. Wonderful. And first, part A is finding the initial velocity of the rock. So we have this lovely little rock right here, and it goes up, and at some point it reaches y equals 15, and the velocity is 25.0. So we want to know this initial velocity. Velocity not velocity and initial. Both are the same thing. So work energy theorem, we rearrange it to get Ki on one side so that then we can substitute in the equation 1/2 mv squared and then substitute in the rest of this stuff, and we'll know that the total work done is just work done by gravity, right? So moving it from it's going up. This is the direction that it's moving in, and the work is the force times distance, but of course the force is going downwards, so in this case, because the force is going downwards, we're going to say that work is negative as the rock is moving upwards. It's going against it, right? So it's negative. So then putting this work total in here, we put in the negative, and the work by gravity is signified by mgy, and you can find that also in the formula sheet here. The large U grav, mgy, that's also meaning U is the potential energy, and this is kind of based on gravity. So you can think of those as almost interchangeable. So we put all this in, cross out m in all of these sections, times each individual part by 2. So we can, and then take, so we basically get rid of these things and then add a 2 here. And then we want to take the square root of all sides, both sides, and we finally find that the velocity initial equals the square root of the velocity final squared plus 2gy. And if you plug that in, you get 30.3 meters per second. And then you move on to part B, which says, what is the y maximum, right? So at y max, then the velocity is going to equal 0, right? So the maximum height, it's not going up, it's not going down, which means that the velocity is in this shifting position, it's 0. So keeping the energy theorem actually just as it is, we want y by itself, so we do the same thing where we substitute in these sections, and I think I forgot to go over here. You'll see here that K, kinetic energy, is equal to 1/2 mv squared. Right, so that will be on your formula sheet, of course, if you can't remember it. Just the same as the potential energy formula is mgy. So here, of course, plugging all of those in, and then you kind of just rearrange the equation. And here, because this final velocity is 0, you can cross out this whole entire section. And we'll just put a 0 here. And then plus, right, this velocity initial squared divided by 2g. And that gives 46.8 meters. That's that question. We'll move on to the next one. Question 51. Which says, while a roofer is working on a roof that slants at 36 degrees above the horizontal, he accidentally nudges his 85.0 Newton toolbox, causing it to start sliding down, starting from rest. If it starts 4.25 meters from the lower edge of the roof, how fast will the toolbox be moving just as it reaches the edge of the roof if kinetic friction force on it is 22.0 newtons? Right, so we draw this lovely picture here. We've got theta. We see that this distance here, 4.25, is the distance from the block to this edge here. So this is the initial point. This is the final point. It's asking what's the velocity at the final point. We know that the frictional force is 22.0 newtons. Of course, the weight is this. Initial velocity, it's starting from rest, so it's 0. The final velocity is unknown. That's what we want. And the final position, right? If position initial is 4.25, then this ending position is 0, but we can also kind of reverse those and say that this is 0.0 and this is 4.25, and I think that should be what we do later. I'll edit this if that's what we do. So with our kinetic energy, kind of just the classic formula, we have the kinetic energy final plus the potential energy final equals kinetic energy initial plus potential energy initial plus the work of other. So any other force, that's usually friction. And in this case, you do see that it is friction, so I put this in parentheses, work of friction, W sub F. Right, and so, you can translate all of these into the components, remembering that potential energy is mgy. So this, we kept this point is 4.2, and so the initial y position is 4.25, and the final y position is signified as 0, and here we say that. So this right, hang on, sorry. Okay, so we know that the initial velocity is 0, so we can cross this whole part out, the initial kinetic energy. The potential initial energy, we just write it as mgy initial, of course. Work other, remember that work is the force times the displacement, or the distance it's the displacement. And so, I'm sorry, I misspoke earlier. So y initial is this distance here times the sine of theta, which is going to give you this y-axis here. So the y initial is up here. It's 4.25 times sine of theta, which will give you 2 point something. And then once it moves down, then this potential energy goes to 0 here. As you'll see, here the y final is 0. which means that once it's here, no more potential energy. So that's explaining that. And then the kinetic final energy, that's going to be 1/2 mv final squared, of course, where the energy of this final point is only kinetic and the energy of this initial point is only potential. And you see that. Plus the friction force. Sorry, the work of friction. So moving all of this down, simplifying the equation, taking out, dividing everything by m, and then we want the velocity final by itself, so timesing everything by 2, and then taking the square root of this side, get this equation here, square root of 2 times, parentheses, gravity times y initial, minus the frictional force times the distance, because of course the friction goes across this entire distance because that's the distance where the box is in contact with friction. And this part divided by this mass, which of course we can find by dividing 85, say 85 divided by gravity, and that will give you the mass, remembering that weight is mass times gravity. Take that and you get 5.23. Then moving on to the last question from chapter 7 is 7.75. And for this one, we're going to move over here. And here you can see the picture that they drew. I didn't think my drawings would do this for figure justice. So here it is. A 350 kilogram roller coaster starts from rest at point A here and slides down the loop. The loop. That's a funny word. As shown here. Right. At A, how fast is this roller coaster moving at point B? And B, how hard does it press against the track at point B, right? So here, if we take this point right here, if we pretend that this is 0, then we're looking at the difference in potential energy here. So we'll say that because this only has potential energy, it's starting from rest. And this one here, if this point is 0, then it has no potential energy, and it only has kinetic energy. And so over here, we've written down all of our lovely equations. We set y final equal to 0, which is the same as pretending like this is the ground. And that means that y final is this height here, 12 minus 12, and then y initial is 25 minus 12, right? Because this here is 25, which gives you 13, of course. And so then it asks for the final velocity, the energy, the master energy formula, really. We remember I said there's no kinetic energy, it's starting from rest, but there is this potential, and there's no friction, no other work done. So we cross that out. There's only kinetic friction on this side. So over here we can rearrange the equation, and 16.0 is our velocity final. Now the second question, we have to think a little bit more and interpret a bit more. So how hard does it press against the track at point B? So this pressure that it has where the cart, let's say that this is the cart, and it's pressing against the track, that's going to be matched by the normal force of the track pressing against the cart, right? So here, if we draw our free body diagram, we have our cart with the mass times gravity going downwards. The normal force is the force of this track pressing against the cart, which matches the how hard the force of this cart pressing against the tracks. And since it is a circle, we have acceleration as centripetal, and of course it's going towards the center of the circle. So then we see, well, first we need the force of the cart against the track here, and the radius of this circle is going to be half of this height, right? So it's going to be 6 meters. And we see that the sum of the forces equals mass times the centripetal acceleration. So the sum of the forces is mass times gravity plus n. We want to isolate n, which means, moving this stuff over here, we input for acceleration because we don't have centripetal acceleration, but we do have this velocity now, right? So this velocity is going to be the final velocity because that is the velocity at point B. And so we plug in all of these numbers and we find that it is 11500, otherwise 1.15 times 10 to the 4 newtons. Moving on to chapter 8. Please allow me to flip the pages since I am old school and have a physical textbook. So this question, right, this also has a picture that we're going to use. Block A in figure 8.38 has mass 1 kilogram and block B has mass 3 kilograms. The blocks are forced together, compressing a spring S between them. System is released from rest on a level frictionless surface. The spring, which has negligible mass, is not fastened to either block and drops to the surface after it is expanded. Block B acquires a speed of 1.20 meters per second. A was the final speed of the block, and B how much potential energy was stored in the compressed spring. All right, so first we want the speed of this second block. So we write out our lovely values. We have mass A, 1 kilogram, mass B, 3 kilograms. The velocity of A and B are 0. The velocity of B, final, is 1.20 meters per second. What's the velocity of the final A? The velocity of A final. So first, we want to remember that Pi equals Pf. Now what is P? That is momentum. And you can see right here, this is the equation given for on your formula sheet, where the potential energy equals mass times velocity. When we're working with multiple masses, they may each have their own velocity, or if they are connected, then they will have the same velocity at that point that they are being connected, or at all points that they are touching. So first, the initial momentum, the initial velocity is 0, which means the initial mass times velocity is 0. The final, we have mass of A going in one direction, and then the mass B going in the opposite direction, so they have to have opposite signs. If we want to isolate the velocity of A, then we move this over, divide this other side by MA, and plug in the numbers. This is what we get. Wonderful. Next, it's asking us what is the, how much potential energy was stored in the compressed spring. So, here I wrote what is the potential energy of the elastic section. Well, if you look on your formula sheet, it's got this elastic here, U elastic, right? That gives you 1/2 k times x squared. But here, k is the spring constant, and x is the distance that it's compressed from equilibrium. We don't have either of those, so we have to make do with summing up the kinetic frictions after they are both moving, right? So the final kinetic forces, the kinetic energies that are of each of the blocks has to have come from somewhere, which is where this potential energy of elasticity comes in. So no initial kinetic energy, no frictional or other work. The second one, there's no potential energy, so we have potential initial equals kinetic final. Now here in the kinetic final, like I said before, we have the first mass kinetic energy plus the second mass kinetic energy. And so then once you sum those up, you get the total, which is 8.64 joules. So then we're almost done. Yeah, 2/3 of the way through. Question 18. A 5.00 kilogram chunk of ice is sliding at 12.0 meters per second on the floor of an ice-covered valley when it collides with and sticks to another 5.00 kilogram chunk of ice that is initially at rest. So first let's write down our values. Mass of 1 and 2 are both 5.00 kilograms. Of course, there should be another 0 here. The velocity of the first one, here, let me go ahead and write in this this other 0. Right, we have another 0 about there. Wonderful. The velocity of the first one while it's moving is 12.0 meters per second. The velocity of the second one is rest, so it's 0. What? Right. Since the valley is icy, there is no friction. After the collision, the blocks slide partially up a hillside and then slide back down. How fast are they moving when they reach the valley floor again? And then it gives you a hint, but the hint says, break this problem into 2 parts, the collision and the behavior after the collision, and apply the appropriate conversion law to each part. So it's asking what is the velocity of when both of the masses are connected and it's going down the hill, right? So according to this way, down and to the left. So first, we know that the momentum initial is equal to the momentum final. That is just a law of physics. And so we can sum up the initial momentums and then sum up the final momentums and use that to find this final velocity here. So mass 1 times velocity 1 plus mass 2 times velocity 2, but velocity 2 is at rest, which means that part is going to be 0, equals, right? So now, because they are sticking in the second part of this problem, we consider it as one object. So, but it's still going to have the masses of both, so you have to sum up the masses and then times the velocity of this new double unit, right? So down here you can see this picture. We have this double unit here going, and so you can rearrange the equation, and then you'll find out that the velocity just after these 2 blocks have connected is 6.0 meters per second squared. And if you look at this figure here, right, the kinetic energy initial is going to be transferred fully into potential energy final over here. And then once it's converted all of its energy, it's going to then start reconverting that potential energy into kinetic energy to get this second final one. Right? So if you're going from, let's say, N to, of course, N in the potential energy form, and then back down, you're going to end up back at N, just in the opposite direction this way, right? So the velocity going down is going to be the same here. So 6.0 meters per second. And this is analogous to, right, the problems that we were working on before, where if you have a rock that you are throwing upwards, right? So if this is a rock, and you throw it all the way up here, and then come back down. If you draw a horizontal line, then this point here, let's see here, oops. Then, oops, well, okay. That didn't work. All right, well, this point here is going to be the same magnitude as this point here. The only difference is it's going to be, right, if it's in this curving motion, then the upward value is going to be positive and the downward value is going to be negative. But they're going to be the same numerically, except for the sign. So it's the same concept here, right? So you go up and then down, and this point here, the velocities are the same. So our final problem is 8.27, which is two cars collide at an intersection. Car A, with mass 2,000 kilograms, here, is going from west to east, while car B, with mass 1,500 kilograms, is going from north to south at 15 meters per second. As a result of this collision, the two cars become enmeshed and move as one car, as one mass afterwards. In your role as an expert witness, you inspect the scene and determine that after the collision, the enmeshed cars moved at an angle 65 degrees south of east from the point of impact, right? So south of east from the point of impact. A, how fast were the enmeshed cars moving just after the collision? And B, how fast was car A going just before the collision? Right, so what is the velocity of the combined masses, and then what's the velocity initial of A? So here, because we are having components and we don't really know this velocity here, we're going to componentize the momentums. So here, the momentum initial in the y direction is equal to the potential final in the y direction. So B here, we have mass of B times velocity of B equals the mass of AB, this mass here, times the velocity of AB sine theta, right, which is going to be this vertical component of the velocity, right? So velocity AB times sine theta is this y component of the total masses, mass AB, velocities. So if we rearrange this equation, we've got all of these values, or at least we can get them. Of course, mass A plus B, that's just going to be the sum here. And we find that the velocities of these enmeshed cars is 7.09 meters per second. And then we move on to part B, which is what was the velocity of A. And we do the same thing, except we take potential initial in the x direction. So here, in the x direction, we have mass A times velocity A, which we don't know, equals this other component. So now we have mass AB times velocity AB. We have both of those now, times the cosine, here, this component of theta. You can divide both sides by the mass of A and find that the velocity A is 5.25 meters per second. So that concludes our sections 1 through 4 of lesson 8 and chapter 7 questions. Good luck on your test, and yes, let me know if you have any questions.